All right, so we have a dense presentation ahead of us. So let's get right into it. So let me say a few words about Denis. The first thing I want to say and make absolutely clear is that a huge pleasure for me to have Denis in person here to deliver the slide. Just for context, why I'm saying this, we've been working with Denis since 2019, and I met in person twice, once for a beer at a conference, essentially, and then through this week at BU where he's visiting, and maybe we'll see him a lot more in the future if things pan out the way I hope they will. No spoilers. The work that Denis is presenting is honestly one of those kind of moonshots that just showed up as we were, poking into the system that we work on in our lab. And Denis is not just a researcher; he's one of the first people that joined my lab, even though physically has been always in UM, so in Germany. He has kind of the grandfather of all the students that now work on FPGA, because he brought in that knowledge of FPGA development, working on simulators, looking at waveforms and so debugging and how to do it, and what are the problems, and how to punch Vivado in the face, right? If you know what I'm talking about. And so Denis has really brought in that expertise that is long lasting. And then as we were working on multiple ideas, we felt that we identified something that could really have a long-lasting impact. And this is the work that he has been started to work on. And in my opinion, it's a game changer in the way we think about the division of tasks between accelerators, CPUs, and data engines. And in fact, this talk is called Tensor Memory Engine. We'll define exactly what that means. But strap in for a ride that kind of questions your understanding of duties of what in a computing system should do what, and what is the right way to write algorithms that work on data items. All right. So without further ado, and without spoiling any of the presentation, I'll let the stage to Denis. So please welcome him.
After the introduction, I feel very old now with all my grandkids. In fact, I'm quite cheap for Renato because maybe that doesn't work anymore. It's disconnected. Anyway,
Try to click on the presentation.
All right, yeah. I was about to say I'm actually quite cheap for Renato because I'm actually working at the chair of cybersecurity system in production engineering at TUM with Marco Cacamo, which is my official supervisor, right, in this PhD journey. This project here that we are presenting is, as Renato mentioned, right, a continuation of a wider project we started in 2019. Also, this project includes all the members of BU, right? So Manos and his team have contributed to this. It's sprung out of a paper we already had in 2023, I think. Right. So I also want to give kudos to Manos and his team for this effort. Maybe put something down. Yes. Yeah. All right. So the focus we have in both our chairs in Munich and here is hard real-time system, right? And especially safety critical ones. Right? So any type of computation system that will interface with humans, right? One of the big constraints being that, of course, you want to make sure that humans stay safe, right? So this kind of things have really proliferated, I would say, nowadays, because anything is computing, right? And you always want them to be autonomous and smart. In fact, even if they have to deal with humans, you want them to be a bit smarter than you, right? You don't want the human defect in your computer. Right, you want something reliable. Because of this, right, essentially, the other way around again. Because of this, right, you actually want to increase the amount of information going in your system, right? You want your system to be able to be deployed in very complex environments, right? Because of that, you want them to have a very good understanding of what's happening around, especially once it's related to humans, right? You may even want to start predicting what they're doing. This, right, essentially translates in the multiplication of sensors you will have, right? And by sensors, the result is that you have an influx of data, right, that is being generated and that probably you want to handle if you have the sensor in the first place, right? In addition to this, you will also want smarter workloads, smarter controls, right? Nowadays, everything is AI, so why not slapping that on top of it? You want to extract as much information from your data to be able to handle things correctly. This is all good, but the problem is that systems, especially embedded systems, will have some constraints, right? We know those constraints pretty well at this point. We have the traditional size, weight, and power constraints, right? And we also have more fundamental limits, right? Once I have a processor, even if I don't have to fetch anything from the memory, the architecture, the ILP I have, and the frequency will just dictate what I can fundamentally reach, right? In addition to this, and especially annoying in the context of hard real-time systems, we want some level of predictability, right? I want to be able to understand how things are going to be done. What is important for us is not only the logical, right, correctness of things, but also the temporal one. It's if I have perfect, optimal, right, moves, but it comes in 10 years, it's worth nothing, right? So given all those constraints, right, and the fact that we actually have a higher demand on what we want our smart stuff to do, right, we may, or this is actually a current trend, right, want to integrate accelerator, right? You want to integrate an accelerator because you just want to perform all of this computation as fast as you can. This is generally the trend that you have, right? And it works very well. Okay. The only problem that you have is that if you want, is an abstract representation, by the way, it's no numbers. If you want something that is highly performant or even highly efficient, right, in terms of energy consumption, if that's a constraint, right, you can design something that is highly specific to your task, right? But then the application range where it can be deployed is very limited, right? So I can have the most perfect AI accelerator for my specific agent. As soon as the game has changed in the AI field, it's useless, it's worse, right? So this is actually why GPUs are actually so successful, right? Because even though they are performant, right, the application range where they are useful is larger than a dedicated accelerator, right? And the best in terms of the application range you can have still remains traditional CPUs, right? This is the orange line here. Because essentially, as long as it's Turing complete, my CPU can do it, right? So virtually, I can do anything. But the performance is quite terrible there, right? Yes, even also, right, if you manage to optimize for specific workloads, right, there are some constraints that remain. They are generally mostly related to either memory or money, right? In terms of memory, if I just take the workload that I have and just translate it to hardware, I will speed up the manipulation of the data, but I still have to get the data from the main memory, right? Unless it can fit on chip, but then that's another problem. And the biggest problem of all, as I said, is the money, right? If you want to integrate this kind of design and integrate this kind of accelerators, right, you actually need to pay for it and it comes at a cost, especially if your application is niche, right? You may not have the sufficient volume, right, of physical space to actually be able to produce ASICs, right? All this to say, right, what is interesting for us is CPUs. Right? So in this context, we are only going to consider CPUs as a processing element. Now, I just want to add two things, right? CPUs are essentially not so bad as I'm picturing it there, right? CPUs have a lot of units that are not always used, right? So the SIMD instructions will provide some level of parallelism that will help you spinning up your execution, right? However, because of some constraint in terms of memory, right, it's difficult to leverage them, right? And it will make a bit more sense later. What we are proposing here can normally be also used with GPUs and accelerators if needed, right? However, that will just extend the scope of the research to a point where I cannot graduate in the next 2 years. So we'll just focus on CPUs.
That's the real constraint.
That's the only constraint. All right, there's a tiny problem with my animations, but let's ignore this part here, right? We know, and I think this is a diagram that you have already seen pretty much everywhere, right? The speed at which CPUs or on-chip computation improves, right, is way faster than the speed at which DRAM or memory technologies in general improve, right? This is actually quite well known. And of course, historically, the strategy for this is add some cache, right? Add some memory in the chip that is fast to access, right? The only problem with those caching systems, right, we made them very, very complex nowadays, right, is that they're only good as long as you play the game. They're only good as long as there is some locality, right? And this locality depends highly on the type of access patterns you have, right? So finally, it's good that everything is complete here. And some patterns are way worse than others, right? One type of pattern that is well known as being quite terrible is stride accesses, right? When, let's say for a matrix multiplication, I'm actually interested in data that may be represented as a column, right? So everything that is in the column, right? Here it looks contiguous, right, visually, but once it's in memory, it will actually be located many addresses away, right? So in this case, when I put data here, right, mathematically it's contiguous, but they will end up in different cache lines and so on, right? So we are not using any temporal or spatial locality there. It's actually quite poor, right? However, the other way around, right? If by any chance it happens that my second matrix is already transposed in memory, right? I have, again, I regain all this spatial locality, that will help me actually not go too much to the DRAM, right? Or be able to use the data when it's on chip to the best we can. This being said, the question we have then is, okay, could we actually leverage the application level knowledge of the data access? In this case, we have a matrix, we want to multiply them. Can we actually have the second one already transposed, right? Can we access patterns in the underlying memory hierarchy to export ideal double, with a little caveat, data locality, right? And by ideal, what I mean here is what the user thinks is the most appropriate, right? I'm not giving any guarantees on what should. We want to achieve this, essentially saying, could we, right, try to reinterpret the way the data is being laid out in memory and the way it's being presented to the software or the CPU, right? Such that it will map better to the elements that are already existing. The way we want to do this, right, is through a hardware module that we call the Tensor Memory Engine, or TME for short, right? The idea is that it will sit on the data path, right, between the core cluster and the main memory. And optionally, if we can provide a nice API to be used that is NumPy inspired, right, this would be actually quite nice. The idea is really that we want to provide something that the user might want, right? I'm not providing the optimal one. It's up to the user to still determine which is the best for him, right? Maybe there are more constraints than just a single. And yeah, okay, here we want to be able, I used matrices before, right? But we want to be able to generalize to tensors, right? And other tensors. A tiny example of tensors for you, because that sounds like a very mathematical word and so on. And in a sense, it's not that complicated, right? It's just it's a generalization of matrices to multiple dimensions. In the same way that a matrix, you can see it as an array of an array. A three-order tensor would become an array of an array of an array, or an array of matrices, right? And then you can keep going like that up to the moment where there's no end, right? Infinitely, essentially. Yeah, the idea for me is the following, right? If I'm fine with doing a matrix multiplication the normal way, right? The way I think is fine, right? The main normally, right? With my software, not touching anything, right? I can just go the normal way, right? I perform the computation here, go through the hardware, the normal road to the DRAM. However, if I want to leverage, right, a TME, right, I actually want to go through the API such that I can access this transposed version of B, which does not really exist in memory, and let TME do it for me, right? This is my objective. I use, of course, the example of transpose all the time because it's very easy to introduce the idea there, but we have a series of operators that we want to be able to support. Those operators, right? Here we have on the tensor, right, the transpose. So you can see from my software CPU view, I just want to access things in one order, right? But in fact, in the memory, it's equivalent as me accessing them column by column, right? On the tensor, there are many degrees of freedom in how I can go through the tensor, right? This is just one example of those. In the same way, right, if I see it per cache line, right, and I'm interested in a subtensor, right, I can simply just see here, okay, each row is a cache line, right? And when I'm accessing this one, essentially I'm just looking at a sub portion of my subtensor, right? And each time I progress up, I go there and there. Okay, the +6 just means that I'm looking at the next 6 elements, right? So those are typical examples of things you would want to do on tensors, right? Yes, the point here, right, being that I could start computing indexes and how I need to jump and so on, but jumps are very costly because then I have branch instructions and so on, and it can just cut the flow, right? Being able to streamline everything should normally help improving performance. Yes, I just want to, okay, how do we do that, right? How are we going to implement this thing? What do we envision? We could do it through software and use a software emulator of a system on chip, right? However, we really want to understand what are the constraints that will happen when we do things on the real system. For that, we decided then to select the next best thing we have to prototype things, FPGAs, right? FPGAs have been traditionally used for a very niche product or prototyping for ASICs, right? However, and that started in the 80s, in 2010, right, we saw the advent of a new way of using FPGAs, right? Essentially integrating FPGAs in an already very heterogeneous system on chip, right? The role it generally has is as a peripheral that can be accessed, right? It can be accelerators, can be peripherals, way to handle sensors and actuators, but most of the time it's a side computation unit, right? It can have very different application depending on which class of computation device you have. It can be on embedded side and it's tightly integrated, or it could already be on the server class with PCIe Express card, right? Yeah, what I just want to insist on is the fact that those things are there to stay, right? And there's strong indication since the acquisition of Xilinx and Altera by AMD and Intel, respectively, that these kind of things will become a bit more prevalent in the server class, right? Though there's just an indication and a bit of guess on my side. Where do we fit research-wise, right? Since I joined Renato, right, on this research adventure in 2019, we have published a series of small papers, right, that look at how we can use the FPGA in this kind of configuration in a different way, right? So instead of creating an accelerator, what if I can actually add this hardware module that I designed myself on the data path, right? Allowing me to have a fine-grained control on each transaction I see, right? And then we can start doing very funny and funky stuff, right? We can start changing the addresses such that it maps better to the DRAM. We can start doing a lot of things. I do not have details to enter this, and yeah, I'm not paid by TUM for that. So if you have questions later on, please come. But also have a bug. The idea is the following, right? So the way it works. In the case of PLIM, right, we want to add our FPGA on the data path. In such case, right, there's a direct access to the data, right? And the software needs to be adapted such that we can directly say, go through the FPGA, and then the FPGA relays this information to the DRAM. Maybe on the way doing some manipulation for it to happen the way we want, right? This is something we have done most of the time, right? And most recently, we have actually adopted a new way of doing things, right? Instead of being for sure on the path, we can maybe be selectively on the path, right? So, the keyword here is that we are adding the FPGA to the coherency domain. Each time a transaction is being performed, right, the FPGA will be informed, and the FPGA decides whether it wants to handle that transaction or not. There's a slight nuance here, right? I just wanted to explain this thing, but at the end of the day, what we are doing with the TME, right, can be applied on this kind of approach or the other one interchangeably, right? Okay, yeah, this is just a small summary of what we did together. I can't skip that one. Yeah, okay, let's have a look at and practice what is happening, right, at the macroscopic level. If I'm interested here in this matrix, right, I want to have to go linearly through it row by row, right? But I kind of know that this matrix is organized this way in the main memory, right? So normally I would go by column, right? I can leverage TME to tell him what to do, right? So I configure TME, and the first step is then let me try to access the array, right? So in that case, the co-cluster, there's a miss in my last level of cache, and ends up being in the interconnect, right? Depending on whether I have a plim or plus, right? Somehow it gets the attention of TME, right? And TME says, all right, I'm going to handle it, right? Let me tell you that I will give it to you, but behind, underneath the hood, right? I will do my stuff. What it does is simply say, all right, those elements, right, as a column, visually they are close, but in memory they are completely scattered, right? Let me fetch it for you, right? And this is exactly what you will do, right? N times the amount of elements that actually fit in a cache line, right? The reason why we think this actually will also help is simply because at the hardware level, we can dictate the type of requests we do to the DRAM, right? So we already have a certain advantage that would not be possible at the software level. We can say, okay, I just want this section of my of the DRAM. I do not need to fetch a whole cache line and have longer transactions, right? Tiny details, but the hope is that it will actually help, right? And then once I have reconstituted my cache line, right, I can share it with the co-cluster. And from the standpoint of the software, right, none of this is happening, right? So from the standpoint of the software, all of a sudden, I just have my cache line, right? And it's transposed on the fly. This is in the big lines how the IP works, right? How is the flow of transaction in my system? I don't know if I should really go into details, the architectural details.
Want to say some details, right? I'm assuming.
Let's do it that way.
Dive in and decide where you want.
I will jump that section. I'll go to the API just to give an idea of things are. We can just enjoy food, and if you have questions or interested, then we can go on that together, maybe. I think that's the best way to proceed. Few slides to skip. All right, API, yeah. Okay, so as I mentioned, one of the objectives is to try to present something that is user-friendly, right? For that, I also mentioned that we took some inspiration from NumPy, right? However, NumPy doesn't do the kind of things we are doing in hardware, so it's just an artificial representation for NumPy. This is just to convenience, try to match it. The idea is the following, right? At first, I will try to define, right, the geometry of my tensor. In this case, again, I keep it simple. It's an 8x8 matrix, but can be extended to n-order tensors, right? In this case, it's limited to 4, but you got it. Once I have defined the shape, right, I can define the slice I'm interested in. I can say, look, out of that, I'm simply interested in a sub-matrix, right, 4x4. And even there, right, once I have this sub-matrix, I don't want to start from the original point, right? I want to add some offsets all the time, right? So now when I will start looking at the first element of my data structure from the standpoint of the software, I will implicitly start there, right? And then I can precise also what is the order at which I want to go through my data structure. In this case here, I'm saying, okay, it goes by index, so core 0, index 0, say, okay, you are the one in the second position. It's the one, then, okay, this axis here would be the first one, right? So I can simply describe things that way, right? Or at least I think it's simple. Naturally, right, I end up with this representation there. I have a set of, once you have defined it, you actually create your tensor object and or structure here in C. And I just make sure I initialize it properly. So that's essentially what those functions there would do. And then I just tell my TME, look, now I'm interested in accessing it, right? I've created the description of it. Now I want you to allocate an entry in the hardware to be able to do that, right? I can do my computation. For the sake of the presentation, of course, it's not that interesting to do what I do, but I'm just summing everything, right? I could do, for example, a matrix multiplication, who knows? Right? And then once I'm done, I can simply release it such that the hardware just release one of the entries and another program in the computer could actually go ahead. All right, in terms of the implementation, right? And by implementation, I mean directly on the hardware. Which platform are we considering before I show you some of the preliminary results we have? we are looking at a AMD Xilinx board, right? The Korea board that maybe some of, I mean, Renato has a bunch of those at this point, which are a PSPL platform as I presented. So here we have a chip where we have normal ARM core, right? A53, which are somehow still considered high performance for embedded systems, right? And they have a tightly integrated FPGA on the side that can run up to 333 megahertz, right? Our implementation of TLE runs at 250 megahertz currently, but maybe there's a way to extract it. I don't know if people are so interested in the specific resources that we have, but here I just want to show you, right, that, okay, we are capable of reaching a certain frequency. We have up to 4 order, right? And given all this capability, right, we have a relatively small footprint on our FPGA in terms of resource utilization. If you only consider RME and not all the bloat on the side, right, it's 8% of lookup tables and so on. It's fairly small. So this is something that could adapt to even smaller system on chip that have an FPGA, right, or smaller FPGA. The idea is the following, right? Okay, once I have that and I prove that, okay, it's small resources for the hardware, right? In what context do I want to use this? So I mentioned that we have a vision of trying to use it for tensor applications, right? And through that, there are a lot of things that are actually doable and a lot of things to explore that I haven't explored yet, right? However, in order to be able to test my hardware and see if things are going fine and try to have a first idea, a first taste of what are the limitations, right? Is there anything that I haven't considered, right? Where do I actually gain? Everything is about nuances, and I wanted to explore this. For this, right, we decided to go for the general matrix multiplication, right? Not that I think we can particularly shine in that application, but it's a good entry point to see what we can do, right? So we started, right? And I think if I ask anyone here right now, take a piece of paper and write down the matrix multiplication, right, in C, Python, or whatever, this is probably what you would come up with, the textbook implementation of it, right? This, right, as I've shown in the example before, will do the job just fine, but it has a problem, right? It has this triad axis over here, right? Meaning that it's going to be extremely, extremely slow. Okay, I use as a baseline this, so here it doesn't quite make sense speed up wise, but it will make sense later. I can already see that I don't have an incredible instructions per clock, right? My IPC is fairly small, I have 3%, right? There, right, my L1 ratio is also quite bad, and same for the L2. Okay, there is actually a nice party trick if you want to speed up a bit the process of doing a matrix multiplication. You can simply, right, zero the memory before, right, but swap the 4K and the 4J, right? And simply doing that, right, makes it a bit nicer on the computer, right, on the CPU. Essentially, you can see I have a speed up of 25, right? Which is not too bad as a party trick. I don't know if anyone is interested doing parties, but those are the kind of things I do. And in terms of IPC, right, we can also see that seems to just be a better utilization of my processor, right? I have a way smaller L1 miss ratio. In fact, I swear I found it, right? It's not missing. It's somewhere over there, right? And the L2 miss ratio is more or less the same, but it seems that it's not a problem, right? If we look at the roofline model, right? But yeah, do you guys know how the roofline model works? I have a slide. Yes. All right. So I'll come back to that later. So the roofline model is a model that comes from our friends at Berkeley, right, in 2008. And the idea is, okay, let's try to understand what is the bottleneck, right? Roughly, in average, the bottleneck of my program on my system. The idea is simple. I have 2 axes. The first one is the peak performance, right? How many flops per second I can have. Generally, it's more like gigaflops for high-performance computer. But yeah, this is the amount of operations I can do a second. On the other side, what I have is my arithmetic intensity, right? The amount of flops per byte. So it will give an idea on how good the locality is, right? Or what is the usage, right? The idea here is the following, right? Fundamentally, I can already draw a line and say that there's a feasible space and unfeasible space because my computer has a limit, right? How many instructions can I do per clock cycles, and what is my frequency? I can already draw and say, all right, this part is completely unfeasible, right? Like physically, it's not possible. On the other side, what I also know is that, all right, my computer is limited memory-wise, right? Even if my layout is fine, so I have a certain bandwidth. Kind of magically, if you do the ratio between your arithmetic intensity and the peak performance, right? Up, you have bandwidth. You have a bandwidth, right? So you can just say, all right, my system has this throughput, right? This is the maximal I can achieve, right? And up, you can draw your memory bandwidth there, right? You could also have, of course, multiple of those depending on what you're trying to look at. And this draw another unfeasible region, right? Because I can't access this, right? I'm limited by the memory of my system, right? By the feasible throughput. And yeah, it is simple. Once I do my, I do some benchmarking and I look at the performance counters, I can have an idea of what are the amount of misses I have and the amount of instructions I'm actually retiring, right? And then, okay, based on where it falls, right, I can say, right, this is going to be memory bound if my dot is close to this part, right? And it's going to be compute bound if it's close to this part, if it's in this region, right? It's kind of a debate a bit, okay, once I have a dot here, what happened, right? Am I memory bound or computation bound? So those ones are pretty clear. Those are a bit less, and some are confusing, right? So there's a limit to what we can induce from this, but it already gives an idea of where I'm landing, right? Of course, this is an aggregation of the data after a whole execution, so it doesn't tell you what's happening in specific segments of my program. So yes, I use this to help me understand a bit better where are my bottlenecks, right? Especially the memory part. Yep. Yeah, so especially the memory part. So if I go back before the party trick, right, and I look at how my naive implementation is performing, right, what I see, this is, by the way, sorry, the bandwidth of my DRAM, right? This is the limit in performance of the core without any vectorization. And this is the limit once I'm using vectorization and vector instructions, right, SIMD. So here I can see the naive one is pretty low, right, in terms of performance, but that we kind of know when I compare against the other one, right? You see it's pretty bad, it's kind of obvious, right? And what I especially see is that my operation, right, my arithmetic intensity is also pretty bad, right? It means that the locality probably is not so great, right? If now I say, all right, this is one cool party trick, but obviously maybe I could do things faster if by any magic, I already have the transpose in memory, right? What happens in that case? Right? Maybe I already know beforehand. Then, right, program is fairly similar to the first one, but the indexing is way nicer on your computer, right? What you see is that you're increasing drastically your performances, right? The green one is the non-vectorized version, right? In this case, I have a higher speedup, I have a higher IPC, so I'm using better my resources, right? Miss ratio, and the ratios of missing is roughly the same as the other one, right? What I see is that the performance is way higher, right? Actually, we are CPU-wise kind of close already to the limits, right? And in terms of the vectorization version, the red one, right? We are then memory bound, right? Here, in this case, the speedup is quite high. One thing is that this is the same code for me that I'm writing. The only difference between those two colors, right? Those two versions, simply adding a compilation time, right? So, okay, now you vectorize things, go ahead and do your trick, right? And so I can actually gain a lot through that because it's already vector, right? Which itself is an opportunity, right? Because if now I can say, all right, let me use my TME, right? And I have the data presented to me in a way that is nice for vectorization, but in fact, normally I would never have this vectorization possible because I would need to access things as a stride, right? I should be able to do it. However, things are never that simple, right? So turns out, if you see the dot line here, this is the sustainable bandwidth of TME for the moment, right? So it's pretty bad. So typically, right, you can see it's the same algorithm as the previous one. So I have the same arithmetic intensity as I would normally have for the two orders, right, when things are already transposed. However, I'm completely bottlenecked by my bandwidth in this case, right? And my 2 points are here, vectorization or not, right? And that translates definitely in at least the speed up factor, right? So the question is, right, what can I do from here, right? And the answer is probably, I would say deceiving, but quite straightforward in the sense that I can improve my hardware, right? I could maybe try to get one clock cycle here and there, improve the frequency, right? But, and we have few ideas on how to do it, right? But maybe the truth is the following, right? Maybe this specific application is not the one that works the best for us, right? So I presented the matrix modification because it's a fairly well-known way to approach things, right? But in fact, what we have to do, at least I believe, right, is to explore a bit where this technology, this way of proceeding, right, may have a usefulness, right? And our current belief is that this will go better once we have higher dimensions, right? Once we have multiple orders of dimension and we start tackling a tensor application, right? Those ones are actually quite a good fit also for us in the sense that they are very difficult to make sense out of, right? I mean, visually, they are very nice and the conception is good, but if I'm trying to optimize my code, right, without having some hardware trick, right, it may actually be quite difficult because things are very scattered all over the place and I may have to introduce a lot of branching just to be able to handle, okay, now I need to wrap and get something else, right? And it's actually, in fact, so complicated that you have very good mathematicians that are spending a lot of time trying to optimize those things, right? But it's difficult once it translates directly on the computer and there's an architecture as a constraint, right? So being able to provide an easier representation to the software programmer, right? So anyone that would want to use and tensors, right, actually is probably where we'll get a lot. Right? The computation is a bit less, let's say, in comparison to matrix multiplication. Right? I just want to add one thing that I've presented a subset essentially of matrix multiplications I've implemented. There are a lot out there, and I have up to 18 different implementations of my matrix multiplication. And yeah, I've wasted a lot of time with that. But you learn quite a lot by doing this kind of things.
So if you can interject right here, I want to stress one thing. So essentially what Denis is saying is, by doing these tricks, essentially what you're changing is the very semantics of memory addressing, where normally when you write your algorithm, the reason why it becomes complex is because you have to link the logical step in what you need next to progress in your algorithm to the position of that in memory. And then you're calculating all these indexes, you have to figure out where to go and fetch the next element you need in the next logical step in your computation. Here, what he's saying is actually, if you just tell me the access pattern in a language which is compact, like the one that you defined there, which is actually what we call a access pattern definition language, we just made it up. If you describe it to the hardware will make appear data that follows the access pattern as if they were logically located together. And so now your indexes is this, the indexing system is what you need next, as opposed to where the thing is located in memory. That's what the advantage. You can run your algorithm and worry about later about making it nicely located. I think good locality.
It's a software engineering assistant, essentially.
If you want.
Trying to help a bit there. So yeah, this is all the kind of questions we are left with, right? And that's kind of the next step for us in the next weeks, I guess. I hope it will not take months to get to the next step, right? But those are things we want to investigate. Where can we fit? Where can we help, right? And also, okay, what can we do to try to make things better? Because as shown, right, there's already some sort of bandwidth constraint that is there regardless. But just something I would want to add before I close, right? This is not the end of the day, right? Because, okay, sure, I'm limited bandwidth-wise, but if I find any algorithm, right, that somehow naturally fits here before TME and can still enjoy what TME has to provide, right? I should have there my improvement, my speeding up, right? And actually, we kind of have found such algorithm, right? There are a bit more advanced version of doing a matrix multiplication. So there's a recursive version of doing things, right? And there's even a tweak to it, right? I think it was proposed in the 70s, the Strassen algorithm, right? Which even reduces the amount of multiplications you need fundamentally, right? So, like mathematically, it's less complex. So I just want to mention that, okay, not we are not yet doomed for the matrix multiplication. I still have some.
So the interesting thing what you just said, that algorithm, if you were to write it, is insane in a sense, in terms of manipulation of index you have to do. So on paper, it's fast. If you implement this, it's terrible. And this is where you can say, all right, well, what if I boost the locality and you?
I have a bunch of backup slides, but I don't have anyone for this one, so that's a bit annoying. But yeah, there's so it's not that complex to implement. It's very tedious to implement, and it's complex to debug if you have a pointer issue, right? So yeah, it can take some time. There are just ways to make things a bit nicer and more than just transposing, which is what we use recently. There's also ways of sub-selecting the matrices, because once you start doing recursion, you're essentially interested in smaller sections. So yeah, I think that's about it for me for today. So I thank you a lot for your attention. I hope this was interesting. And if you have any question, please let me know, whether it's now or afterward, I'm there. And if you're interested in the architecture itself, just let me know, I'll stay around.
Why don't we do the architecture?
So we have some time. So now I was waiting for you to get sleepy with the food, so that you can doze off in the architecture's part. If you want, we can dive in. We can take questions, however you want to handle this. Maybe we can start diving in, and then the question will start to roll in. But there's already one. All right, good question.
So there are some matrix multiplication algorithms that are supposed to be the fastest, but they are fastest in terms of the least amount of multiplications. They're faster than Strassen, right? The problem is usually they're bad in locality, and they don't use the fastest known matrix multiplication algorithm because it's actually slower on real hardware. This is
so there is all those so-called galactic algorithms, right? Which essentially definition means in terms of mathematical complexity, it's amazing. If I have to implement it, it actually won't be as good as some of the well-known versions, right? Essentially, even that recursive algorithm, right, has a problem that you need to select a subsection of that matrix, and it requires you to copy-paste things, unless you want to go in the very deep game of trying to accumulate indexes and smart managing them, right? Which ultimately TME would help with. Now, even when you do the recursive, right, the mathematical way says, all right, you go all the way down to the point where you only have one element per matrix, but it's just a number, right? Turns out if you do that, it's terrible, because since it's recursive, you have your stacks that just your heap that just increases, right? So what you want essentially is one point to detect, right, for your specific architecture, where to stop, and just do the normal naive matrix multiplication, and it's actually just fine.
That's what they do. They
actually do that. Yeah. So depending on the processor you have, or if it's a GPU and so on, right, you may just have a different way where you stop going down, right? The Strassen is exactly the same order of IT, and I think most of the galactic algorithm go that way.
Not sure, but I know that it's like 2. To the power 2.7 versus 2.3.
So the Strassen algorithm is 2.8 something. So it's a big O of n 2.8.
And the fastest is 2.3.
So the naive one is 2.3. 2.3, okay, yeah. But probably doesn't scale that well.
Architecture?
Architecture? People are interested in architecture. You had a question?
Yes, I had a question. So the reason that your TME implementation right now is not as good as the other one, could that be because there is a sunken cost we're paying when you are accessing and reorganizing all the data, and you don't do enough operation with your new shiny cache line to recoup that cost?
So matrix multiplication is at the end of the day quite nice in terms of like what you want to show, but it has one inconvenience, let alone is that once you pay the costs, right, to get the data reorganized, right, you're essentially discarding it almost, right? Okay, maybe you reuse it, but maybe if your matrix is too big, by the time you want to reuse it, you have to go all the way down to go through TME again, right? So if now you have, right, algorithm that will reuse this reorganized data, of course, you pay the cost only once, right? So if now you increase the locality of reorganized data, then of course you should be able to mitigate, let's say, the cost, right? At this point, it's a mitigation game. I would say.
That's exactly why I think going to more complex algorithm like CPLS, algorithm, alternate least square, decomposition algorithm for high order tensors. That is where this thing is gonna
So
shine.
basically, you're doing more operation.
No,
per
not
cache.
single operation, but you access the same object, the face
More
of tensor, which could be very large, through different modes. Like sometimes you want a slice, sometimes you want a column, sometimes you want a fiber, sometimes you want a subtensor. And this is where you can register them in parallel. And then this one will access them.
Because at the end of the day, it's the same data, but just different
Correct, so
level of
different views,
accessing.
correct, different views of the same exact in-memory object without aliasing, without copying this object multiple places and then having to maintain
Just
consistency.
have to reorganize that data.
Correct, the view with a different, different angles, right? If you want
Just to add one thing, right? This thing was part also of your question. There are two ways to progress here that are fairly orthogonal, right? I can improve my hardware, right? And that will benefit I will benefit from it regardless of the use case. But then, of course, like exploring really where, what are the algorithms where I will gain and will benefit, right? Itself is the other part, and it's completely orthogonal to one another. There are constraints in my hardware that I didn't have time to present, maybe later, apparently, where, okay, definitely we think that, all right, we have created, because of simplicity, some bottlenecks, right, that can be resolved, right? How much there is to gain? I won't try to guess, right? I'm a scientist, so unless I have numbers, I don't speculate, right? So I'll just not do that, but we can only gain at this point. That's the only thing I would say, right? Hopefully, we gain. Yeah.
architecture too.
Have you looked at like maybe like tree-based data structures or anything? Like for example, like I'm saying like B plus trees, sometimes they're pretty good locality, depending on how wide you make every element.
Yeah, so for trees, right? I think most of the time they're implemented with pointers, right? So you have maybe some locality in each node, right? But at the end of the day, you will have to do a lot of pointer chasing, right? Which, I mean, essentially, right, we could have a machinery that also handle pointers and does pointer chasing for you. But that also is yet another level where we can do things. And it's a bit more complicated at this point because you need information about also virtual to physical addresses, right? If you're doing things at least with an operating system, if you do things bare metal, maybe it's easier.
So actually, a follow-up on that, there is this thing which is cache-friendly packed B plus trees or variations of B plus trees that essentially they have way fewer pointers and they could benefit from just fetching the necessary. So essentially, you know which node you are by the location in a memory array, essentially. So we could actually think.
Okay, this is something we can.
This is an interesting.
Okay.
Because the pure pointer chasing can be, it's a different problem, I think.
It's another class of
But
problem.
this is the right way to think about this, right? You have your computing engine and you have your data. Normally, you burden the computing engine with also figuring out where to fetch the data. And here we say, no, you can actually decompose it to things. You can have something that strings the data according to access pattern that you want and present in the best way possible is friendly to the caches. In fact, it's friendly to the prefetchers. In fact, it's friendly to the compiler when it tries to auto-vectorize your code. So you turn an access pattern is n-dimensional, potentially n nested loops into always one loop, right? One sequence of accesses, because everything is just the next element you need.
Yes, there was a question over there. So.
Yeah, I have a much more interesting use case for you.
Okay.
Have you ever tried accelerating oblivious algorithms using this technique?
No, that's not something we have.
So what you describe, so the problem you're trying to solve here is a big problem in secure computation in general. So in secure computation, you're actually trying to hide the access patterns.
Yeah.
Don't leak information about the data. And the way people do that is essentially they have algorithms that perform exactly the same access patterns for all inputs of the same size. So the access patterns do not depend at all on the input data. Right? So you know exactly at compile time how you're going to access the entire data set.
I think, okay, so I think what you're describing is actually the reason why Denis might be here in the future.
Yeah.
It's actually expanding on this, actually, we think we can, and I mean, not reveal too much, but I think we can create some secure computation paradigm that uses these tricks.
at least so we've been building a system that uses a bunch of these oblivious algorithms. One example is bitonic sort. Right? So I don't know if you could accelerate bitonic sort with that. Another example is odd-even aggregation.
Well, one thing you can do is actually the opposite, meaning you implement your algorithm by accessing sequential things, but actually what you're accessing is obfuscated by the hardware.
So
We could hash the addresses and that would be one way, but at the same time, it depends on where's the location of the module, right?
So these algorithms, by definition, they actually access data which are scattered around. I mean, they do multiple passes typically over the input table, let's say, but they essentially compare. You can think of it as comparing rows in a table which are far away from each other. And I guess using your approach, you could. So currently, what we're doing is that we copy these rows into a consecutive, chunk of memory, and then we do something faster.
But let me put it this way: with this approach, accessing the same exact element
Yeah.
at a different point in time could correspond to two completely different memory locations.
Say it again.
So let's say you have an array,
Uh-huh.
it has the element 1, 2, and 3, and then
Yeah.
go back 1, 2, and 3. Actually, the actual data contained in element 1, because of this, could be completely different the second time you come around and you access the array.
Okay.
So in a way, you can create something that looks, completely sequential, but the actual data underlying that gets fetched at every time is completely different.
I think that would be good. We should talk more.
Yeah.
I have an unrelated question. So, is this expected to perform well with sparse data as
No.
well, or it's only for dense data?
It's only for dense data structures. Maybe that's something I should have.
Which is excellent because in secure computation data are dense.
All right, perfect. Yeah, my research is not to say that.
That's directly.
And
The other thing
You
is-
heard it right? We do this through coherence. So here, we really get snoops from the caches and we interact with the snoop commands coming from the caches. This is at the level at which he's playing with the caching subsystem.
If you can repeat.
Other questions?
You still want to see some of the architecture, or you heard enough?
Apparently, you want us to see it, so let's.
No, I mean, you know that before, and now I'm
I
asking
said, but
you
I don't know, it's already a question, so I'm happy either way, right? It's fine.
We have 5 minutes.
We should take a vote. Who's going for, want to see some architecture, and who has enough?
It's fine.
Thank you very much, Jen.
All right.